So up front, again, if you're still trying to get in the class, go see Angie in 441 West Hall. And we have started, please. Thank you. No labs next week, no class on Monday. So no labs meet next week. The pre-lab number 2, it's open now, so you can do it whenever you want over the next week and a half. Just have it done before your second lab, which is, of course, the 24th through the 26th. Office hours have started, not too many questions coming in. But even if you have a question about SPSS or the pre-lab activity assignment, or as you're looking at the practice homework, you are welcome to come over and ask a question. The practice homework that's open now is just practice. It's under the required homeworks, just so that you can go through that process of what a required homework looks like. But it will not be counting towards your homework grade. So if you end up not doing it, that's totally up to you. When you log in as your student username and password, you should now have a homework in the current assignment listing. And the little pencil means you're ready to work on that homework, or you are able to print out the homework questions to bring with you if you wish instead. In editing the homework, there should be a running number of questions on the left. Gives you a countdown to when it's due, when it is a required one. You are able to print out the questions with your answers or without. Select any particular question on the left and it'll bring you to that question. Some of them are multiple choice, as the first one is here. And you just simply click on the box and it'll enter your answer in the answer box. Some of them are multiple choice with one selection, so if you try to select more than one, it'll tell you, don't do that. Tell me which one you really want. Unselect the one you don't want. Some of the questions require entering some text. There's a couple more. One is a multiple choice and the other is picking from a set of answers, picking more than one. You are able to just simply check the box, let you pick more than one, and it records your answers as they're coming in. Those two are not the correct answers to select because you can't have an observational study and an experiment at the same time. But you can deselect any one you don't want also. And the third question is having you find a graph and uploading it. And for that, you need it to be a JPEG or a GIF, those kind of formats. You are able to browse them for the image and upload it, and you get to click in an answer to describe what's the variable that that graph is displaying. What is that response variable? To type that in. And of course, then what kind of graph is it that is being shared? When you type in an answer, you have to save. If you don't save and you go click another question and start working on it, it won't save what you typed in there. So for typed in answers, you do have to save what you want. If you save it, and then you can just simply go back over it and edit it again to fix up what you didn't want there. And there will be at some point places where you might want to put in an X bar or a P hat and things like that, and those symbols are right there for you. So this is again a practice set of questions for you to try out and see how that process works. It'll be automatically submitted for you, and the GSIs will be grading it just to give you feedback on your actual answers, but also for you to see how that feedback will come back to you. And you'll be able to view the solutions as soon as the homeworks are submitted within a few minutes after that. All right, so that's the homework. It's practice only. There's some details, lecture book support, sent out a message this morning, and had some best practices in there, and a few other things to remind you about. The real homework will open up next Thursday, homework 1, and there'll be, I think, 4 homeworks before your first exam, 1 every week. Those will be up to 30 points. This one's just, I think, 5 points only. So they will be a bit longer with some good practice questions to help you prepare for those exams. We're going to finish up Chapter 2, highlight big ideas of Chapters 3, 4, and end today with a 5-point practice clicker quiz. Questions that you can see, are you getting 4 out of 5 correct? So you've got the Chapters 1, 2, 3, and 4, but mainly 3 and 4 somewhat mastered. We'll do that at the end today. So do you have a question or comment before we turn to our last couple pages of Chapter 2? Question or comment at all? If there are any in the back that would like to come get a seat, you're welcome to. There's definitely some seats in the front here. Please find a seat if you'd be more comfortable sitting rather than in the very back. There's a seat right here. There's a seat right there. One there and there. Thank you. So those of you that have a seat next to you and you're in the middle, if you would just sit next to that person when you come in, then it won't be quite so much walking over. There's one in the front, there's one in the second row. Who else has a seat? Down here? Thanks, guys. All right, let's look at our material together today. Page 19 is where we ended. We were looking at a standard deviation as a measure of spread or variation. The interpretation examples on page 19 will be very helpful for your real homework one. The standard deviation is a measure of spread that reflects how far away the values are from their mean on average. It's often then reported along with the mean as a measure of center. And then we have this nice rule on page 20 that works when you have a mean and a standard deviation for your quantitative variable, and the model, the distribution that you're seeing from the histogram, is somewhat bell-shaped, somewhat unimodal, bell-shaped, symmetric. Then we've got an additional rule here that gives us a good frame of reference to work with. And it goes as follows. So if you had your histogram that smooths out to be roughly bell-shaped and symmetric, where would the mean be? Right in the middle, right? And your standard deviation is a yardstick. It's an amount that you can go out from the mean. A standard deviation represents that average distance. So if you were to go out from the mean, one standard deviation each way, one standard deviation each way, you would find about 68% of the observations having values in that range. If you were to go out an additional average distance each way, 2 in all, 1, 2, and look at the proportion of people in that range, you would see that that's about 95%. And if you were to go out 3 average distances, you should have just about everybody in that range, because it's an average distance. And if you go out a couple of them, you should get more and more, but at some point, it should be just about everyone. 3 average distances each way would be 99.7. It's called the empirical rule. In some books, it's called the 68, 95, 99.7 rule. It tells you the percentages within 1, 2, and 3 standard deviations. It allows us to have a better frame of reference. If someone ends up being more than 3 standard deviations away from the mean and it was bell-shaped, that's a pretty unusual observation. So let's take a look at how we can complete a couple problems with this rule. And I guess the main thing that maybe I would box off or highlight here is that what does it work for? Only distributions that are bell-shaped. It wouldn't apply to something that's quite skewed with outliers. In fact, the mean would probably not be used there to measure center compared to the median. That would be better. So the example we have from the text is regarding amount of sleep again for college students. A model to describe that distribution for the amount of sleep has been characteristically bell-shaped, centered around the mean of 7 hours. And the give or take, the standard deviation is a little less than 2. 1.7 hours is our standard deviation. So we got the 3 statements here that correspond to that empirical rule. 2 of them have been completed that you can check on your own. But how would we fill in the blank here to make this sentence correct? 68% of the college students typically sleep between, in what range? 68% means we want to go out 1 standard deviation each way. We want to start at the mean of 7 and go plus and minus 1 standard deviation. One of those 1.7s each way. And then we change that to 2 or 3, and we've got the other values that are there. 7 minus 1.7 takes us down to 5.3. And if we add the standard deviation to the mean, we would get an upper bound of 8.7 about 68% of the college students typically get between 5.3 and 8.7 hours of sleep. About 95% get between 3.6 and 10.4 hours. Just about everybody should get between 1.9 and 12.1 hours. That would be going out 3 standard deviations each way. So is there anyone out here who did not get between 1.9 and 12.1 hours of sleep last night? No one's raising their hand. I had one person in my class yesterday raise their hand, just one out of the 400 some. So it should not be too many. All right, 1, 2, and 3 standard deviations. Can you draw that picture? Let's complete that for this model here. We've got a nice bell-shaped curve. If I put my curve down, I know that when I'm out at the ends here, close to where the curve hits the x-axis, that should be about 3 standard deviations each way. So I'm going to put my mean right in the middle. I'm going to put tick marks. I want 3 going out on each direction to represent 1, 2, and say 3 standard deviations. And then the values that we have from the previous work can be put along here. 7, 8.7, 10.4, and this largest value of 12.1. This is amount of sleep in hours. And on the lower side, we went down to 5.3, 3.6, and all the way down to 1.9. Now I have a very nice picture of that distribution. If I know it's bell-shaped, I know the mean and standard deviation, I can draw the axes and curve fairly accurately. I can also start to see that if I got 9 hours of sleep, I'm somewhere between 1 and 2 standard deviations above the mean. If I only got 4 hours of sleep last night, then I'm definitely on the low end, more than 1 standard deviation below the mean. Just a couple hours of sleep puts me way down here. We can see where we are relative to the mean in terms of that average distance. So what if you did get 11 hours of sleep? 11 hours of sleep is up here somewhere. What do we know about a person who got 11 hours of sleep? First of all, I'm jealous of that person. It's been a long time since I've gotten 11 hours of sleep, but they are what? More than 2 standard deviations above the mean. Let's actually work out how many standard deviations from the mean that person sits. So the 11 hours is above the mean. If you take your observation and you subtract the mean, you're seeing how far away from the mean you are. And that would be 4 hours difference. If you divide that by your standard deviation, you now are looking at how many standard deviations away from the mean your observation sits. And this would turn out to be 2.35. More than 2, but less than 3, as we saw in our picture. And it's positive because we're above the mean. And what if you were a person with just 5 hours of sleep? You're now going to be below the mean by about how many standard deviations? How would you work that one out? You always take your observation first. You subtract the mean and divide by the standard deviation. And now we get a negative, about a negative 1.2. If we were to calculate that. So the sign on this quantity tells you whether you're above or below the mean. Then the magnitude of that quantity tells you how many standard deviations above or below the mean you are. What we've just calculated twice here now is a standard score or a z-score, which allows us to make comparisons relative to that distribution. And if you were comparing your score on your stats exam to someone else's score on their chemistry exam, and they're different distributions, but both somewhat, say, bell-shaped, and you could work out your mean and standard deviation, you could see which one did better relative to that distribution for that class. Converting to a standard score gets rid of the units, and it puts you in the right perspective here. So the standard score, z-score, is always taking your observed value, subtract the mean, and divide by the standard deviation. Allows you to make comparisons, to know who did relative to their model or distribution better or worse. And then you just have the empirical rule given to you again at the top of the next page in terms of the z-scores. Plus or minus 1, 2, or 3 standard deviations gives you that 68, 95, and 99.7% of the values. So you already have a few percentiles known for such models just by knowing whether it's 1, 2, or 3 standard deviations away. Let's try that out for one last example here about scores on an exam. got a nice mean and standard deviation to work with. We are told that we have what we need. We have scores on a quantitative scale that are following a bell-shaped distribution. We have the mean and the standard deviation. We don't have all of the individual scores to look at, but we have a model now that describes that variable. Rob is one of the students in this class, and we are told that his score was 2 standard deviations above the mean. So what was his score? Numbers are easy to work with. Standard deviations, 10. 2 of those going above the mean means he sat at a score of 90. If you have to work it out and the numbers are not so nice, if you're 2 standard deviations above the mean, you take the mean and go plus 2 standard deviations, giving us our score of 90 points. With a standard deviation of 10, any kind of calculation here is not too bad, but if the standard deviation is 1.7, might have to work things out a little bit. So how well did Rob perform? I mean, he was above the mean, 2 standard deviations above the mean. Can you tell me about the proportion of students who must have scored higher than he did? What would that be? Maybe draw this picture here. We've got 70 in the middle. Put a couple tick marks again on each side, and here's Rob's score at 90 over there. 2 standard deviations above the mean. So when I think of 2 standard deviations, what number do you think of from the empirical rule? 95%. 68 is 1, 95 is 2. So was there 5% that scored better than he did? 5% is still on the outside in both directions, if you take it that way. So what do we have? Here's 2 standard deviations above the mean and 2 standard deviations below. We know from the empirical rule that the percent that scored in the range of 50 to 90 points must have been about 95%. And I want to know what proportion scored higher than he did. What was the number of people out here, or relative to that number of students in the class, that proportion? If about 95% are in between here, that leaves 5% total. So how much right there? About 2.5%. So just because it's a 2 standard deviation away doesn't mean the answer is 95 or 5%. Depends on, again, which part of the distribution you're working with. So what was Rob's percentile? You know how you get a score and sometimes you get your percentile? What was his percentile here? Pretty good one, right? There's that 95% here, but then there's another 2.5% here. So his score is the 97.5th percentile. Rob's score is the 97.5th percentile. And so you could do that for 80 points on the exam, or 50 points, or 40 points. You could tell me what percentile it is. You could tell me what percent scored higher or lower than those values, just knowing this empirical rule with a couple of cut points. Characteristic by that standard deviation. The standard deviation measures those typical distances, and it doesn't take more than 3 of those average distances before you've got just about everybody in that range. All right, any questions? Empirical rule. Nice frame of reference. We'll use that quite a bit later. We've got a summary of the various graphs that we've looked at. Some that you have seen, some that you have not yet. We handled all the categorical side. We talked about bar charts. Your numerical summaries are frequency tables that tell you the count or the proportion or percent. We've handled in lecture together histograms and box plots. Box plots were great for identifying outliers for us, but not so great at showing the shape compared to a histogram. In lab number 2, you will see these 2 graphs, QQ plots and time plots. That's what your pre-lab 2 is about. You know, when you draw a curve over your histogram, it kind of looks bell-shaped, symmetric, but it's not perfect. And one of the characteristics we're going to want to know is whether or not that really does have that empirical rule behind it. Does the normal distribution, which will be called later, fit? And a QQ plot helps us to fine-tune, does the histogram look close enough to that bell-shaped model so we can call it a bell-shaped or normal distribution. So we'll look at QQ plots in lab, and then a lot of data is gathered, and it's not just gathered right at the same time point, but rather over time. In fact, sometimes we're looking at trends or patterns or changes over time. If you measure a quantitative variable over every week for the next 8 weeks, you look and see if there's a pattern there. Time plots allow us to take a look at that. And since we often look at data gathered over time, sometimes we need to make sure that over time it's just kind of randomly varying to call it a random sample a bit later. So you'll see those two graphs. Scatter plots come up in later chapters. In fact, I had someone ask the other day, we're skipping chapters 5 and 6. They are two that we're going to cover, but they get covered with the inference material later that corresponds to them. So we will come back to 5 and 6, which are relationships, and scatter plots are present in there. All right, that's our chapter 2 material. Now hopefully you had a chance to maybe just read through the chapter 3, 4 notes as my email out to my classes requested. I'm going to just run through and highlight very quickly some of the ideas that were there, and we will complete the ones that we didn't have finished in the notes for the ones that I posted that were nearly complete. And it's chapters 3 and 4. And that's what your 5-point quiz, practice quiz at the end will be about, this main material. So let's do a quick overview. Chapters 3 and 4 help you to understand if you got good data. Chapter 2 gives you the data, says summarize it in appropriate ways. Make a graph. If the graph looks reasonable, maybe calculate a mean and a standard deviation. But where did that data come from? How was it collected? Can we use it to make inference? We've been focusing on the descriptive side in chapter 2. We have calculated a couple statistics in chapter 2. Anything you calculate on a sample, like a sample mean, or a sample median, or a sample standard deviation, are all statistics. They're calculated on the sample. They are used to tell you something about what you think is happening in the population. When you go the next step, inferential statistics, you're hoping that your sample that you took represents your population so that you can draw a conclusion about what's happening in the population based on what your sample told you. Your sample is a few balls selected from this basket or population of all possible balls. You're interested in learning about some variable. Sometimes there's a response variable of interest compared to the explanatory one. But you're trying to learn about the mean of that population, or you're trying to learn about the proportion of balls in the basket that said yes to that opinion question. And you take a few balls from the basket, a few people selected for your survey, and you get your results of your sample. How can you use that to infer what you think is happening in the population? If your method of gathering that sample is sound, if you don't have bias in the wording of your question, well, then your inferences might extend just fine. It helps us to learn about the world around us. So, one thing I do like about this text is their fundamental rule. When can you use data for inference? Because sometimes the data is provided for you. You aren't designing the study from where the data is gathered, but rather you have the data and have to summarize it. And when is it reasonable to draw inference from it? Well, it states here, can we consider the data we have representative of that larger population with respect to what you're measuring? So the key is not only what is the source of your data, where did you get these people that are part of your study, how did you interview those people as part of your survey, but also what did you ask them? The couple examples that were worked through were the first two. They were both regarding the same question of interest, about whether we have a majority in favor of lowering the drinking age. And the first one talked about what if we have opinions for a random sample of adults from the state regarding this issue. Well, I'm trying to learn about whether or not a majority of adults in the state would favor this, and I've taken a random sample from that population. So it's quite reasonable to use even just the 1,000 adults that we surveyed to tell us something about what we think is happening in the population of all adults. That's much larger. The second example that parallels that was asking the same question and taking a random sample, still a random sample, which means we use statistics to get this random sample, but they were a random sample of parents of high school students, adults who had high school students. And since the question you asked them relates to directly their students and affects them, that's probably not going to be able to be extended. You won't be able to use it for inference. Now, if the question they were asking of this random sample of parents of high school students had nothing to do with the fact that they have students that are in the high school age range, then it might be fine to use those adults as a random sample of the larger population of adults, even though they came from the high school student population. There's adults there. So it depends on what's being asked. So on our last example that wasn't worked out, we are looking at relationship between pulse rates and smoking status for college-age students. Do college-age smokers have higher pulse rates than the non-smokers? So we have a theory we want to put to the test. And the data that we're gathering, it's for college-age students. So we have at our disposal here a nice large random sample of college-age students that are in my class. And I have you measure your pulse rate and record that and click in on whether you're a smoker or not. And honestly, take that data and look at the rates to compare them. Would it be reasonable to use that available data to answer this research question? What do you think? Did we take a true random sample of all college-age students? No. But is there anything to indicate that you wouldn't be representative of college-age students, especially when I'm measuring pulse rate and smoking status? Right? You have, are there freshmen through seniors in here? Right? Males and females, all different majors, minors, and all kinds of regions where you came from and lived. Good variety here. So it's probably reasonable because I'm measuring pulse rates. Now, if I were measuring, do you know what a standard deviation is? You would have an edge over the general college-age population being in this class, perhaps. So the question here is whether we can use this data. Does the fundamental rule hold? And our answer would be probably yes. It would be reasonable. Although we don't have a random sample, not a random sample, and I usually abbreviate random sample with RS. Just not write it all out. Although a random sample not taken, right? The variables that were measured, pulse rate and smoking status, are probably representative of those for the college-age population. What we've measured are likely to be representative for the larger college-age population that we'd like to draw inference about. There are times when you can't take what is called a true random sample. Here's a frame, everybody in your population, give them all a number, pick some numbers randomly, and select those people, send them the survey or whatever. You may not be able to even list the actual frame. But sometimes you can still consider it to be representative of that larger group. All right. Now, even if you do have a representative sample, there are other ways that things can go wrong. Bottom of that page just simply says sampling does give you good answers most of the time if you do it in appropriate ways. You don't have to take a huge, large random sample, but larger usually indicates somewhat better. We'll talk about that. But there are other ways that bias can enter in besides the sampling. There'll be sampling variability, but you can have bias in your results through one of three main categories. Most biases can be under one of these three categories. A bias means that the answers you're getting are typically too large compared to what the truth is, or the answers that are coming in are going to be, on average, too small, underrepresent or overrepresent. They can happen by the way you selected your participants. So how did you select them? Sometimes the selection will produce a bias. Big truckload of oranges come in and you just pick out some of the oranges from the top to see if they meet their standards for accepting that big batch. And what about those ones that are on the bottom? They're hidden underneath and not readily available. You can always have non-response. Non-response bias can occur because not everybody that you wanted to include in your sample answers the questions or turns in that survey. Or some of them choose not to respond, which is their option. So there's always that potential. So you often want to look at the results and hope that they might report in their write-up what the non-response rate was. So you have some idea. Was it only 30% of their sample responded, or was it 70%? And then there's response bias. You ask the question, almost everybody answers, but the way you worded the question or the ordering of the questions in the survey can lead to different answers. Even who asks the questions can be misleading, depending on the nature of that question, if it's a sensitive issue. So there's lots of ways where your responses are coming in, but they can be misleading too. Depending on what you ask, some people might not answer honestly. So those are some issues. Let's take a look at a couple examples and determine which of these three is the primary problem in this description of a study. So one of them is where a magazine is sending out a survey. They do take a random sample of subscribers to their magazine, and they ask them about how often they get that magazine. Would you like it reduced from biweekly to monthly, or keep it the same? So of those three different categories where bias can enter in, which one would be the most issue here? We don't have a whole lot of detail, so we don't know much, but what would be it? Selection. They have a random sample of their subscribers. They would have that listing or frame, so that's probably fine. Response bias, I mean, the question was asked quite naturally here, letting them have the option of keeping it the same and not giving preference to one or the other. So our issue here might be what? Non-response. Non-response. You'd want to take a look at who are the people that are not responding. Would they have a tendency to answer in a certain way that might be, then the responses coming in be misleading? I sent a survey out to alumni that graduated with a SAT major, asking them, what are you doing now? Where are you working? You know, wanting to promote how well a SAT major gets you a job and so on. Who are the ones that are going to answer back? The ones that are working and doing well and using their statistics in their job or whatever, right? So I wouldn't get responses from some of those others that maybe aren't using their stats at all or not employed at the moment or whatever. All right, that would be response and non-response bias here. What about the second one? We take a random sample of registered voters that we contact by phone. We ask them about whether they're planning to vote in this upcoming election. What do you think? The contacting by phone is not so much of an issue these days. A couple good examples in your text to look at. One of them is about a very historical survey done many, many years ago, and not as many people had phones. Only those that were more prominent in society had a phone. And the results coming back from that survey were not predictive of the result of the election. Here would not be an issue. You have random digit dialing devices that can dial residential phones or a cell phone very readily. But you ask them whether or not they're planning to vote in the upcoming election. What are people going to say?
Selection bias.
Selection bias because what?
People are already registered to vote.
Well, a lot of people are registered to vote, right? And out of that group, they're trying to figure out how many are going to actually get out to the polls. So they do want to look at those that are registered, perhaps, okay? Let's assume that's the population. Response bias then, perhaps, right? What are people going to say to this question? Of course I'm going to go out and vote. Is everybody actually going to go out and vote? No. And so you get an idea here of the response bias. In fact, we'll look at some actual data a little later to look at the magnitude of that response bias. People will have a tendency to say yes, even though they may not actually end up voting. What was their pattern of voting in the past? That's typically indicative of what they might be doing in the future. We will look at the results after an election is over, asking them whether they voted or not, and looking at the actual turnout rate and see how different that is from our random sample and what percent said they did vote compared to what percent of voters that were eligible to vote actually did. All right. When we give you a question like this, we're looking for the most prominent one that comes out from that question. You can always come up with examples of, well, if this happened, there would be this bias. But look for the prominent one coming out. You take a sample of 1,000 to 1,500 people, and you can estimate the proportion who have some characteristic pretty accurately. Say within 3% of the truth, most of the time. A lot of sample surveys out there are trying to learn about what proportion of people would say yes, what proportion of people have this opinion, what proportion of people would vote in favor of this issue. They're trying to learn about the proportion that have a certain trait or an opinion. And that symbol for that population proportion is P. P represents the population proportion who have a certain outcome or trait. It's the quantity that I want to know. But in order to know that number, I'd have to ask everybody in the population and get that true rate. Not possible. So we take a sample. We conduct a survey. and we look at the sample results. And if we calculate the proportion in the sample that have that trait, that may or may not be the true proportion. It is represented by p hat. The hat over a quantity usually means it's an estimate of that quantity. That is our statistic that we would compute. And it is a quantity that is going to hopefully get us a pretty good answer most of the time. We can quantify how close a sample proportion would tend to be to the true proportion in most of the samples through its margin of error. Have you seen margin of errors reported with surveys before or election results? Usually it's on the bottom, a plus or minus 3% or something like that. Well, that margin of error tells you an upper limit of how much your sample proportion would tend to differ from the truth for most of the samples, for 95% of all possible random samples. The proportion will vary from one sample to the next. We hope it varies close to the truth, and we can say that 95% of the results would tend to be within 3%, or whatever that margin of error is of the truth. Now, what's nice about the one-only formula from chapters 3 and 4, it's an easy one, 1 over square root of n. That's the margin of error for estimating a rate, a proportion. It's a 95% level of confidence, 1 over square root of n. Now, we just learned a 95% just a minute ago. It was in that 68, 95, 99.7 rule. If we were to go out how many standard deviations? 2. We would have a range where 95% of the value should be. Well, that 1 over square root of n is really 2 standard deviations. And when you take 2 times the standard deviation formula, it reduces to a nice 1 over square root of n to remember easily. So what we do is we know that our sample proportion probably isn't the truth. So we'll take our best guess, that sample proportion, and rather than just saying 56% of all eligible voters are in favor of this issue, well, that's based on my sample, let's give you 50 whatever percent plus or minus the margin of error, giving you a range of values that are quite reasonable to think that the true proportion would be in. So let's try it out. Here's a poll result for 1,250 adults. Many questions were asked regarding the American public school systems and rating that. One overall question was, in general, would you rate the quality of American public schools to be excellent, pretty good, only fair, etc.? And these are the counts. For the response being school quality in a categorical response, not on a numeric scale. So if I were to ask you what kind of graph might you make of these results, I'd hope you pick a bar chart or a pie chart would work. Here's the table of frequencies or counts, and make a bar graph with maybe the height being the proportion or percent. We're going to use this data to estimate the proportion of all adults who think the schools are excellent. What proportion of our sampled adults rated the quality to be excellent? Well, there's the excellent category. How many said excellent? 462. What proportion reported excellent? Now, these are all the answers here, so the total does add up to 1,250. So there is the proportion. Here's where a calculator would come in handy to be able to summarize it a little better. 0.37, or we could write 37%. Now, what did we just calculate here? We calculated a sample proportion. So the symbols that we just talked about, P or P hat, which one is the right one here? P represents the true or population proportion, and we just calculated a P hat. The sample proportion who said excellent for our one random sample of 1,250 adults. What if we sampled another 1,250 adults from the same population, roughly the same time frame, and asked them to do the same question? Would we get exactly 37% saying yes? Excellent. No. It'll vary. Next time it might be 42%, or it might be 37%. It'll vary. So how do we have much faith in this number right here? Why would we say, let's estimate the true rate to be 37%? Well, it was based on 1,250 people, which should tend to give you an answer that's pretty good most of the time. Let's actually work out what that margin of error is to reflect how far off it might be from the truth occasionally. 95% margin of error, the easy formula is what? 1 over square root of n. So here again is where a calculator would be needed. 1 over the square root of 1250 is less than 3%, 0.028. There's our margin of error. It's a 95%. It's a little conservative. We'll show you that aspect a little later. We're going to show you how to be 99% confident, any level of confidence you want, and if you want to be conservative or not, we have a different formula for that. But the conservative version at 95% is so easy to remember. Any survey you see out there, you at least report the sample size, you can kind of get that margin of error very quickly. So what's a range of reasonable values for that population proportion? Yes, 37% is my best guess, but I'm going to give a nice range around it that I can be pretty confident that I think the true proportion might be in there. I would estimate the population proportion of adults that say excellent to be somewhere between, let's do 37%, and go out our margin of error each way. We'll add and subtract off that 2.8%. So the range would be 34.2% all the way up to a little less than 40. Does it look like I have more than a third of all adults saying excellent? Would you be pretty convinced at that? Are all the reasonable values for the true proportion above 33%? Mm-hmm. Does it look like I could say that I have a majority? No, not at all. I'm not even near that 50%. Not even 40% is a reasonable value. These are the reasonable values. I am 95% confident that the population proportion is somewhere in here. Confident in it. Now the true proportion, that population proportion, is either between these two numbers or it's not. It's some true number, I don't know what it is, and it either falls in between those two numbers or it doesn't. But I'm confident of my range because this procedure we just used gives you intervals like this one, and 95% of those intervals do have the true proportion in them. 95% of the intervals like that do end up having the true rate in them. Only 5% end up missing. I'm hoping that one's not one of the missing ones, but I don't know. But I'm certainly giving you a range that's fairly precise, and I'm 95% confident about it. If I wanted an interval that I can be 100% confident every time it has the true proportion in it, well, 0 to 100%, and that's not very precise at all. All right. The hardest part is not calculating your interval. We just did it. You can calculate 1 over square root of n. The hardest part is kind of understanding what that 95% really means. It's a 95% margin of error. The interval that we just made either has the true proportion in it or it doesn't. No more probability. The probability that our interval we just made has the true proportion in it, it's either in there, probability 1, or not in there, probability 0. But the interval I used is the method I used to make that interval is a good method. The procedure, if it were repeated, produces a lot of intervals. And 95% of those intervals are going to have the true rate in them. So that's why I'm confident about the one I have. That's a little harder. We're going to look at a really nice simulation that will demonstrate that for you in one of your pre-labs, I think number 3 it is. Yeah, pre-lab 3. So we'll focus on that a little bit more and highlight that along the way. The last two ones on that page are already filled in the notes. They basically work with that margin of error a little more. And the margin of error is what again? 1 over square root of n. It only depends on the sample size. It does not depend on how big your population was. Your populations are big. Take a sample size of 1,000 or 2,000. 2,000 will be better than 1,000, no matter what size the population was. All right. Couple last big ideas. We've mentioned the fundamental rule for using data. Ideally, we'd like to be able to say that our data can be considered a random sample from your larger population. All of the inference techniques, including that confidence interval idea we just went through, require a random sample. Now, we relax that to say, does a fundamental rule hold at least? But the idea is we want the properties like a random sample. For random sample, I'm going to later talk about IID. If you have a random sample, then those observations are IID. What does that mean? That means they're independent observations. So the answer you get from the first person that you survey should not influence the answer you get to the question that you ask of the second person that's selected. No independence, or no dependence, independent. And then the other part of this, the ID part at the end, is identically distributed. That really just means they came from the same basket, the same population. Identically distributed. If I conduct a survey over the next week about opinion of some issue, and then in the news at some point midweek there was some major event that might change people's opinions, well then the population I'm really surveying from is changed in terms of the distribution of opinions. I want to make sure that the model and the population I selected my data from is all the same one. We'll be checking that idea with time plots. So once we go through that in your second lab, we'll be using time plots, because you gathered your data over time, to make sure it looks somewhat random and not some trend that says the population model's been changing. So we'll talk about that. Those are the properties you want. Otherwise, you've got the volunteers. I mean, how many of you have seen those surveys on commercials or TV shows where they let you call in to give your opinion? Yes or no? Well, first of all, you have to be watching the show, be willing to pay the 50-cent rate or whatever it applies to call in. And so those are volunteer samples that are conveniently taken and not very scientific. Many good shows state this is not a scientific poll when they report those results. And I like this last example. Tainted Truth is a book by Cynthia Crossan. Oops, why is my pen not working? And she reports on a number of interesting studies. One of them was showing the extent to which people do not like to say they don't understand the question or they don't know what the question's about. They still answer it. This particular example had a study of American attitudes towards different ethnic groups, and they purposely put in an ethnic group in the list that was made up, the Wissians. And it came back that 30% of the people who filled out that question and survey had an opinion and ranked them up and among the other ethnic groups that were listed there. So they had an opinion of this made-up group because they didn't want to pretend like, I think I remember hearing about that group. No. So they didn't want to ask. There's the extent too. You can ask the questions, but you can ask questions about events or issues that people that aren't in the news and maybe people don't know about, and they might still answer. All right, so I will ask you to read through those couple sections. They are some interesting examples to look at. Here are your pictures of the day to introduce your couple Chapter 4 ideas. Chapter 4's notes are even shorter, just 2 pages. How do we learn? So when you talk about a study was conducted, there are 2 basic types of studies. One way we learn is through a study that is an observational study. The other way we learn is by experimenting, playing in the mud. Observing and experimenting. Observational studies. You observe, you record. You don't ask them to do anything different as a researcher. You record their behavior, their opinions, their ideas. Experiments. That's where the researcher can manipulate, can assign you to a treatment and have you take that treatment because you've given consent and agreed to be in the study. And then you look at the outcomes. You see the effect of the treatment on the outcome more directly. Experiments versus observational studies. You can't always do an experiment. You can't take babies that are born, break them up into 2 groups and say, you guys are going to smoke and you guys are not, and we're going to look at incidence of lung disease or whatever afterwards. You have to observe that instead. Observational studies or experiments will typically have variables that are measured in the study. We already know the type they are, whether they are categorical or quantitative. But sometimes they play a various role in the study. Sometimes they are the response variable, the outcome of interest, what we're trying to really learn about. And then other variables we measure might play the role of being explanatory. I want to know the effect of one variable on the other. And then there are other variables that I measure, demographic results and so on, that I'm recording because I want to try to avoid confounding of my results. I want to look to see whether gender really had an effect on the outcome. So when I control for that or correct for that, do I still see the same link between the explanatory and the response. Confounding variables are variables which weren't primary of interest. They weren't the explanatory that you're trying to see the influence on, that response, but they are related to the response and maybe the explanatory too. And if it turns out you have confounding variables and you didn't measure them, well, then you can't control for them. You don't know if the outcome you're seeing is due to the change in the treatment or because of this other variable, which also differs in your subjects. You can't separate out the effect. They're mixed up. So that's why we record a lot of other variables. That's why you see results in health studies that talk about we controlled for weight or age or these other factors. They weren't the primary variable of interest, but they measured them and have ways of adjusting the results according to them. And all of those variables out there that are confounding but you don't know and you can't measure them are called lurking variables. Those can be a problem more so in the observational side because you aren't able to control for them there. You can measure them and help in that respect, but experiments where you randomize your subjects, if I truly randomize, then my two teaching methods taught to two different classrooms should have about the same proportion of males or females in the two groups, should have about the same proportion of freshmen versus seniors in both groups. The randomization should help to balance your treatment groups with respect to those potential confounders. So at least that balance is there. All right. You have two examples to identify observational study or experiment. The first one was completed in the notes that were posted for you. This is where we just simply recorded how many times a student visited the health center and recorded their diet and their amount of exercise in two different categorical explanatory variables. It was an observational study. Our last one we'll do together before we turn to our little quiz is on the next page. Does the color of the paper that your exam is printed on make a difference? Does the type of question make a difference? I would say that one, yes. If it's a hard question versus an easy question, that would influence scores on the exam. What about color paper? They were looking at these different clues, different external clues, and how it influences your performance. So they had two different variables, the color of the paper and the type of question, each at two different levels. And they had them all take an exam. They were randomly assigned to one of those four different possible combinations and measured the outcome. So what kind of study do we have here? Is this based upon an observational study or is it a randomized experiment? Observational study, you just record. Randomized experiment, you give the treatment to the subjects. You assign the treatment to the subjects, and that's what was done here. We have four different treatment levels or combinations. It was a randomized experiment. When you say that we assigned the subjects to the treatments, then it's an experiment. Not always is random assignment used, but that's a good feature in a experimental design. All right, so we have these different variables that are measured. One of them was the color of the paper. What role does it play? Is it the response variable of interest or the explanatory one? Explanatory. And what type is it? Categorical, with two different types. All right, and how about the other variable here of exam score? That would be the response variable, the outcome of interest, and it is a quantitative. Score out of 100 points. 100 points with no half points is definitely discrete, but if there's 100 points possible, I might treat that somewhat on a continuous scale because there's so many values that I have to record if it were discrete. Quantitative, though, is correct. We would probably look at perhaps box plots side by side of the four different sets of scores to see whether color of the paper and type of question had any influence. All right, very good. Last question here is having to do with the fact that the ones that got the blue paper were mostly upperclassmen. The ones who ended up being in the red paper group were mostly the lower class. So class rank could make a difference. Older know more about taking exams and have a little bit more experience in that case. Then class rank, although not the primary outcome of interest, might be what kind of variable here? The word was confounding. Is the doing better on the blue paper, if that were the case, due to the fact that we're more upperclassmen who took the exams on the blue paper, or is it due to the fact that blue paper is just better than red? We couldn't separate out the effects of class rank from color of the paper. They would be mixed up. All right, so now give you a little bit of time to get your clicker out and ready. If you have a calculator, there could be a formula in there somewhere. If you don't, your neighbor might have one you could borrow for that one. I'll let that one go a little longer. You've got always a blank page at the end of your set of notes for any chapter. You could use that to write out your answers on. I will post these slides by the end of the weekend, so you don't have to write down the question, but it might be good to try writing down your A, B, C, or D options that you pick so you can see your score quickly at the end. So 5 questions. I will not be showing you the answers right away. Next Tuesday, I will. All right. 5 short questions. Each of them have some choices. Some will go more quickly than others. You do have your chapter 3 and 4 notes in front of you. I sometimes hear in some of those questions some page flipping, and that's fine. But if you do try to take all 5, having just gone through the review and you get 5 out of 5, that's a good sign. I will post the slides up on the weekend so you can see the questions again. Next Tuesday, you will see your distribution of scores for this class, because I'll save those points for looking at that. All right, so our first question. Question number 1. There we go. Most statistical inference techniques require the data to be what? You pick your A, B, or C. Most statistical inference techniques require the data to be. All right. I'll give you a 5, 4, 3, 2, and 1. I'll try to move that over a little. Question number 2. When a representative sample is selected, but only a small proportion are actually able to be contacted after many attempts, the problem is called what? You're looking up definitions, aren't you? Now, I'll let you talk on this quiz, but in an exam room, you'd not be able to do that. All right, let's do a 5, 4, 3, 2, and last call. All right, and our next question. Question number 3. Random sample of 400 college students. 30% have said they have allergies. I need an approximate 95% confidence interval for the population proportion of all college students that have allergies, if you can. All right, we're getting close to our last call here. 5, 4, 3, 2. You have a 1 in 5 chance of getting it right. And 1. We'll close that out. The last 2 questions are about the same study. So the description is given in the first part of the question here. Question number 4. Looking at whether taking vitamin C helps to prevent colds. The researcher randomly selected 500 subjects, recorded whether the person had regularly taken vitamin C over the past month, and whether they experienced a cold over the past month. She then compared the percentage that experienced a cold for the 2 groups. So this is the background of the study. You're supposed to identify here whether it's observational or experiment for the first question. And then there'll be a follow-up one for the last question about this study. All right, 5, 4, 3, 2, and 1. All right, last question coming up. The last slide after that is the answers, so you can see how you did immediately. I will be saving the results and show you next week. It pertains to the same vitamin C study and asks you regarding to identify the explanatory variable. So in that vitamin C example of whether the vitamin C prevents colds, the explanatory variable. 4 choices here. Give you another couple seconds. 2 last slides, the answers, and then just the reminders again before you head off. Should get about 300 responses. 5, 4, 3, 2, and 1. Here is your set of answers. See if you got 5 out of 5 or 4 out of 5. Right there. CCBAA. Ooh, ooh. All right. And my last slide of announcements. That was a great job. We'll have your summary next time. So no labs. Look at that practice homework. Watch that email that came from support@lecturebook. Have a question, come up front. Otherwise, have a good weekend.